So section 2.3 is entitled Characterizations of Invertibility. So this section is all about what we call the invertible matrix theorem. That's what most textbooks call it. Our textbook doesn't, I don't think our textbook gives it this name, but I'm going to call it the invertible matrix theorem. It says the following. Let's say you have an n by n matrix, so a square matrix. Then the following statements about this matrix are all equivalent. So first of all, A is invertible. So what are alternate ways of saying A is invertible? So number one, A is invertible. That's the main statement. So what is another way of saying this? A is row equivalent to the identity. That means A can be row reduced to the identity. That's number two. Number three, A has n pivot positions. Number four, the homogeneous equation AX equals 0 has only the trivial solution. X equals the 0 vector, so only the trivial solution. Number five, the columns of A are linearly independent, or you could say the set of column vectors is linearly independent. Number six, the linear system AX equals B has a solution for every vector B in Rn. That's the same as saying that A, the coefficient matrix for that linear system, is invertible. What else is the same as saying that A is invertible? The columns of A span Rn, or the set containing the columns of A spans Rn. And then number 8, there's an n by n matrix C such that CA is the identity. And number 9, there's an n by n matrix D such that AD is the identity. And number 10, A transpose is invertible. So each of these 9 other statements is the same as just saying A is invertible. So I'm giving a proof strategy for how I'm going to go about proving this. So the idea is any of these statements, so I have all my statements listed 1 through 10. I should be able to get from one statement to the other. So for example, let's say I wanted to get from 1 to, 5. I could go follow this arrow. No, that's not a good way, right? You can't go back against that arrow, so that's not a good path to take. I'm going to take this arrow, and then I can take that to get from 1 to 5. So I should be able to go from any statement to another statement following the arrow. So that means I'm going to have to prove these equivalences and these implications. I'm going to start with the equivalence, 1 if and only if 2. 1 if and only if 2. Where is that? 1 if, it's this, right, double arrow. Oops, erased. It wasn't supposed to erase. So when you're proving a double arrow, that's called an if and only if. When you have a double arrow, that's an if and only if. You have to prove both directions. You should be able to go both directions. Sometimes you actually don't have to prove both directions, though. Sometimes you can just say if and only if, based on, well, we'll see. So I want to prove 1 if and only if 2. So remember what 1 is. 1 is A is invertible. 2 is A is row equivalent to the identity matrix. A can be row reduced to the identity matrix. We want to prove those two things are equivalent. Well, actually, we've proven this in class. No, not in class, on the videos, right? We had a video, previous video, where we proved that A is invertible is the same thing as saying A is row equivalent to the identity matrix C. So we're just going to say, note, A is invertible. That's 1. If and only if. 2, A is row equivalent, or A can be row reduced to the identity matrix. So I'm just going to state that, right? That's a fact that we've proven before. We showed this in a previous video. So it's already proven. Also in your book, it's Theorem 7, page 109. Okay, so 1 if and only if 2 is done. Next, it looks like I go into 2 if and only if 3. Where is 2 if and only if 3? This double arrow right here. So what's 2? Two is, oops, A is row equivalent to the identity matrix. 3 is A has n pivot position. So we have to show that A is row equivalent to the identity matrix if and only if A has n pivot positions. So we're going to start with 2. A is row equivalent to the identity matrix. Okay, so I'm going to write A is, I'm going to put the squiggly mark instead. A is row equivalent to the identity matrix. I'm going to just write if and only if A has n pivots. Why is that true? Why is that an if and only if statement? Well, think about it going from left to right. Start with A as row equivalent to the identity matrix. So if A reduces to the identity matrix, think about the identity matrix. How many pivots does it has? It has n pivots, right? It has a pivot in every single row. There are n rows, so n pivots. Now, think about going the opposite direction. Let's say we start with a matrix A with n pivots. Well, if it has a pivot in every single row, that means you could turn every single pivot into a 1, and you can get zeros below and above the 1. So you're going to get the identity matrix if you row reduce it. So there's really no proof there. It's simply fact. So we don't have to really prove much there. 2 if and only if 3. Okay, I will just add a little explanation. A is row equivalent to the identity matrix if and only if A has n pivots, since, I'll just give an explanation, since the identity matrix IN has n pivots. There's not much to prove there. Okay, so 2 if and only if 3 is done. Let's go into 1 implies 3. 1 implies, no, I'm sorry, 1 implies 8. 1 implies 8. It's going to be in yellow. Oops, it disappeared on me. It wasn't supposed to disappear. So we're doing a one direction this time. 1 implies 8. So how do you prove 1 implies 8? So you're going to assume 1, and you're going to work your way to 8. So we're going to assume A is invertible. 1 implies 8. Suppose A is invertible. That's what we're assuming, 1. And we have to work our way. We somehow have to work our way to 8. We have to show that there's an n by n matrix C such that C times A is the identity. What does it mean for A to be invertible? Well, according to the definition of invertibility, then there exists an n by n matrix. Call it whatever you want. I'll call it C, such that CA is the identity and AC is the identity. So there's some matrix you can multiply by A on each side, the left side and the right side. It gives you the identity. C is actually A inverse, right? Now what do we want? We actually wanted to get 8. What's 8? That CA gives you the identity, so we got that right there. So we're done. That's pretty much the proof. Don't have to do any more work. Okay, what else do we want to do? We got 1 implies 8. 1 implies 8. Let's do 1 implies 9. Where's 1 implies 9? That's, don't want to get rid of that. Okay, 1 implies 9. I'm checking them off as I go along. So this arrow right here, 1 implies 9. So we're going to assume A is invertible, and we're going to show there is n by n matrix D, such that AD is the identity. So 1 implies 9. So suppose A is invertible. That's what we're starting with, 1. Statement 1. And we want to show that there's an n by n matrix D such that AD is the identity. Okay, what does it mean for A to be invertible? So since A is invertible, well, by definition, that means there's a matrix, an n by n matrix, you can multiply A by on each side to get the identity. Let's just call it, rather than C this time, let's just call it D. You can give it any name. We know it's the inverse of A, but let's just call it D. Since A is invertible, then there is an n by n matrix D such that AD is the identity and DA is the identity. Okay, so what do we want to get? We wanted to get AD as the identity. Do we have that? Yeah, right, we got that right there. That's what we wanted to get. We wanted to get that there's an n by n matrix D such that AD is the identity. We're done. That's the proof. Okay, so that's done. What do I want to show next? I have 1 implies 9. I want to show 9 implies 6, I think. 9 implies 6, so that would be... ooh, don't want to get rid of that. This long arrow here. 9 implies 6. So what's 9? There's an n by n matrix D such that AD is the identity. 6 is AX equals B has a solution for every B in Rn. So 9 implies 6. So how do we show 9 implies 6? So we start by assuming 9. Let's remember what 9 is. There's an n by n matrix D such that AD is identity. So suppose there is an n by n matrix D such that, what was it, AD is the identity? Yeah. Equals the identity matrix. Now, if you were to go back, problem 24 from page 103, so by problem, this was a homework problem. I actually did this in class. This is in section, I believe, 2.1, at the very end of section 2.1, page 103. By problem number 24, page 103, if you let M be equal to N, if you suppose that there's an n by n matrix D such that AD is the identity matrix with M equal to N, then it follows that. What does it follow that? Well, number 6 follows. AX equals B has a solution for each vector B in Rn. So in the problem number 24, we were using M. We were talking about Rm, but now we're just changing it to M. So I'm saying let M be the same as N. Okay, so we basically already did that problem, previous homework problem. So I'm not really proving anything new here. Just reciting old stuff that we've already done, basically. And next I want to do 8 implies 4. 8 implies 4. Where is that? That would be this one here. So where is 8? 8 is right here. There is an n by n matrix C such that CA is the identity. And 4 is AX equals 0 has only the trivial solution. So we're going to assume 8, there's an n by n matrix C such that CA is the identity. So suppose there is an n by n matrix C such that CA gives you the identity. So that's what we're assuming, and we want to get to number 4. What do we want to get to number 4? AX equals 0 has the trivial solution. Well, if you go back to problem 23, so by problem 23, from this was section 2.1, I believe. This is page 103. This was a homework question. I actually did this one in class with if you let m be equal to n. So in the book, they were using m. Here we're just going to let m be equal to n. That means then, how did it go? The homogeneous equation, AX equals 0, has only the trivial solution. I'll say x equals 0. So we proved that in class. So, okay, I'm just reciting old stuff. So that was what 8 implies. Oh, I forgot to draw the arrow. 8 implies 4, I believe. Yeah. Oh, that's what 4 is. AX equals 0 has only the trivial solution. Okay, what else do we want to do here? How about 4 implies 3? I'm checking off all these arrows as I go along on my strategy guide. 4 implies 3. So where is that? 4 implies 3. Right here. Checking that arrow off. So what's 4? AX equals 0 has only the trivial solution. So we're going to start with that. We're going to assume that. And we got to show what 3. You have n pivot positions. A has n pivot positions. So let's assume AX equals 0 has only the trivial solution. Suppose AX equals 0 has only the trivial solution. Okay? So, what does that mean? If you remember the different statements for linearly independent vectors, that means by equivalent statements for linear independence, remember, AX equals 0 has only the trivial solution. That means the columns of A are linearly independent, right? That's another way of saying the columns of A are linearly independent. Another way of saying that was saying that there's a pivot in every column, right? So by equivalent statements for linear independence, A has a pivot in each column. Not row, column. Pivot in each column. And each column, I'm going to underline column. Now, what are we trying to get to? We're trying to get to 3. What's 3 about? 3 is about having n pivot positions. Well, if we have a pivot in every column, right, and there are n columns, that means we have a pivot, we have n pivots. Thus, A has n pivots. And that's what we wanted to prove. Okay, so we got 4 implies 3. So I've checked that off. What else do I want to check off? I got 4 implies 3. How about, let me see here. How about 6 implies 3? Where is 6 implies 3? This one. Oops. So I'm going to start with 6. AX equals B has a solution for every vector B in Rn. I'm going to start with 6. I'm going to prove 3. A has n pivot positions. Okay, so 6 implies 3. So we're going to start with 6. Suppose AX equals B has a solution for each B in Rn. And we want to prove that there are n pivot positions. So if you remember the equivalent statements for spanning Rn in this case, and before we would say spanning Rm, but we're now changing it to Rn because we have, rather than m rows and n columns, we have n rows and n columns. So by equivalent statements for spanning Rn, right? If AX equals B has a solution for every vector B in Rn, that means the columns of A span Rn. And another way of saying the columns of A span Rn was that there's a pivot in every row, right? By equivalent statements for spanning Rn, then A has a pivot in each row. I'm going to underline that word row. Now, how does that guarantee we have n pivots? Well, remember, there are n rows and n columns. So if you have n rows and you have a pivot in every row, then that means you have n pivots. So thus, A has n pivots. Okay. So that's 6 implies 3. What else do I have to do on this diagram? I got most of the arrows taken care of. Got 6 implies 3. Any others? How about 4? If and only if 5. We need to take care of that one right there, right? This double arrow right here. 4 if and only if 5. So 4 if and only if 5. AX equals 0 has only the trivial solution, x equals 0, if and only if A1 through AN is a linearly independent set. Well, that's just from the conditions of linear independence. So 4 if and only if 5. This is true by the equivalent statements for linear independence. Equivalent statements for linear independence. So we don't even have to worry about proving that. 4 if and only if 5. What other things do I need to do here? How about 6 if and only if 8? Is that right? 6 only if. 6 if and only if. Do I have this written down right? That's a 7. Okay, 6 if and only if 7. Oh, this one right here. Oops, erased it. Six if and only if 7. 6 if and only if 7. So 6 is AX equals B has a solution for every B in Rn, and 7 is the columns of A span Rn. The set of columns spans Rn. Well, those two are equivalent, 6 if and only if 7, by the conditions for spanning Rn. So we don't even have to prove that one again like the last one. So 6 if and only if 7. 6 if and only if 7. We know that's true by equivalent statements for spanning Rn. All right, so have I taken care of all the arrows? No, there's this last arrow here right on the side. What's this? 10 if and only if 1. 10 if and only if 1. Okay, so I got to prove 10 if and only if 1. I'm going to prove 1 implies 10 first. 1 implies 10. And then we're going to prove 10 implies 1. So if I'm proving 1 implies 10, I have to start with A is invertible. So let's suppose A is invertible. It follows that then A transpose is invertible. This is proven in class. Or in another video, let's say in a previous video, right? We proved if A is invertible, then A transpose is invertible. And A transpose inverse is A inverse transpose. So then A transpose invertible proven in a previous video. That does that. A is invertible, then A transpose invertible. Now we got to start with A transpose invertible and prove A is invertible. So let's suppose A transposed is invertible. Well, by using that result, if A is invertible, then A transpose is invertible, then you can transpose A transpose. So it follows that A's transposed, right? The transpose of a matrix is invertible, right? So if I take A transpose and transpose it, that must be invertible, is invertible. Right? If the transpose of a matrix is invertible, and we know AT is invertible, then ATT is invertible. And what's another name for ATT? We know that's A. So that proves that A is invertible. That's it. We got 1 implies 10, 10 implies 1. So we got all the arrows taken care of. So that's the end of our proof. I'm going to put a box to indicate that's the end of the proof. So we've proven every single arrow here. So that's the proof to the invertible matrix theorem. In the next video, we'll do some examples